Next, we will discuss the different forms of energy. The different forms of energy explained below falls under sound, chemical, radiant, electrical, atomic or nuclear, mechanical, and thermal energy. Sound energy is, for example, voices or whistles. It's something that we can hear. Chemical energy is a glue of atoms together. It's a potential stored in food. It's chemical reactions that release heat, for example, when striking a match or combining vinegar and baking soda to form CO2 gas. Energy is released. Radiant energy, it's combined heat and light. For example, sitting next to a campfire or a light bulb. Electrical energy is a movement of electric current through wire. Energy changes form, typically to mechanical energy, then mostly to thermal energy in the form of heat. Atomic energy is produced when atoms split and releases a lot of energy, for example atomic bombs or nuclear power plants. Mechanical energy is a potential to move and moving energy in terms of kinetic. Thermal energy is disorganized energy. We have sensible heat and we have latent heat. In a class, in an exercise, please discuss the following forms of energy and determine whether or not they are potential or kinetic, and whether perhaps they might be both. Sound is kinetic energy because we have moving waveforms. Chemical energy is potential energy. It's stored energy that's waiting to be released. Radiant energy is kinetic energy because we have heat moving in the light in waves, and we have light moving in waves. Electrical energy is kinetic because we have the flow of electricity through wires, conductors. Atomic energy is potential energy. Energy is waiting to be released as soon as a particle is split. Mechanical energy can be potential or kinetic energy, depending whether or not in which state it is. A car standing still has a potential to move, and a car moving is under kinetic energy due to the velocity. Thermal energy is kinetic energy. As soon as a temperature change occurs or phase change, there's change in relation to its normal state. Next, we will discuss the flow of energy. First, we will look at energy conversion. We have useful energy and not useful energy, where energy not useful is classified as entropy because it is in a chaotic state. Useful energy can then be broken down into the theoretically available energy and the actual available energy due to losses in efficiency. The practically available energy can be determined as exergy. Exergy is the energy that is available to be used after the system and the surroundings reach equilibrium. The exergy is usually zero. Determining exergy was also the first goal of thermodynamics. Exergy is neither created nor destroyed during a process. Energy changes from one state to another as in the first law of thermodynamics. In contrast, exergy is always destroyed when a process is irreversible, for example, the loss of heat to the environment. This destruction is proportional to the entropy increase of the system together with its surroundings. The destroyed exergy has been called anergy. A simple example of exergy: air at atmospheric conditions of temperature, pressure, and composition contains energy, but no exergy. When it is chosen as a thermodynamic reference state known as ambient. Individual processes on Earth, such as combustion in a power plant, often eventually result in products that are incorporated into the atmosphere. So, defining this reference state of exergy is useful, even though the atmosphere itself is not at equilibrium and is full of long and short-term variations. Types of energy flow. There's three main types of energy flow, meaning conduction, convection, and radiation. Conduction is a transfer of energy from more energetic particles of a substance to the adjacent less energetic ones as a result of the interaction between the particles. As a temperature difference causes flow of energy from higher temperature to cooler temperature. Convection. You have natural convection and you have forced convection when, for example, a fan is blowing air over a hot piece of metal. It is a transfer of energy between a solid surface and the adjacent fluid that is in motion, or combination effect of conduction and fluid motion. Radiation is a transfer of energy due to the emission of electromagnetic waves or photons, both visible and invisible. For example, the sun rays, where we can see the light and we can feel the heat. What makes radiation unique is that there is no contact between bodies, and this can be achieved in a vacuum as well. The wave striking a body transfers energy, agitates molecules, and in turn heats up. The fundamental energy flow processes. Here we have surrounding air at 20 degrees, a small solid body at 60 degrees, and a large solid body at 20 degrees. Between the surrounding air and the small body, and even not the large body, because they are the same temperature. So only between surrounding air and the small body, convection will occur. Between the small body and the large body, conduction will occur. Radiation will occur from magnetic fields generated by the small body being hotter than the surrounding air. Energy, systems, and surroundings. Here we have two liquids, water and milk. The water is generated to steam in order to go through a heat exchanger or system and heat up the milk from a cold milk to a hot milk. The system has a thermodynamic boundary which is drawn over the area where the heat transfer between the water or steam and the cold milk is achieved. This generates three questions. Can the thermodynamic boundary move? The answer is yes. If it is a movable boundary, this boundary can move. If we add another heat exchanger further along the system, or heat recovery system, the boundary will move. Can the transfer to the surroundings change? As the temperature increases and decreases, more and less losses are achieved to the surroundings. Can a phase change occur in the system? Yes. When water is generated into steam, a phase change occurs, and again when the steam cools and water is produced, another phase change will occur.